Hey, thank you. Thank you for the invitation. It's a pleasure to speak in this conference. I'm sorry I couldn't make it to be there in person. Yeah, so everything I'll say today will be based on some recent joint works with a bunch of clever people. So first one's my colleague here in Atlanta, Ernie Krut. Jun Zemao is a PhD student at Georgia Tech working with Ernie. My good friend Adam Sheffer, a New York local, professor at CUNY. Kyle Eep, postdoc at Georgia Tech, currently in transit. I think he moved to Hong Kong. And two other PhD students, Sung Chung Lee from South Korea and Daniel Zhu, PhD student in Princeton. Yeah, so kind of my goal today will be to tell you a little bit about some recent developments, about some topics related to Sidon sets in the squares, some Erdős problems about repeated distances in the grid and related sets, and the so-called Elekes-Ronyai problem. So kind of the way I envision this talk to go, I thought I would tell you first about two classical facts about two sums of squares, which maybe most of the people in the room have seen before in some way or another. These go back to Landau and Ramanujan and maybe some others before that. The first one is this classical estimate regarding how many integers in a given interval from 1 up to x you can have that you can write as a sum of two perfect squares of integers a and b. And it's well known that the number of such integers m is on the order of x divided by square root of log of x. In fact, even more precise information is known nowadays, but it's we know a prime number theorem analog of this with the right constant called the Landau-Ramanujan constant. But for the purposes of this talk, just the fact that there are roughly on the order of x over square root of log of x such integers m in this interval is enough. The second estimate, also as far as I can tell, first in writing by Ramanujan, but this one I think most likely is did some other people before, concerns how popular you can have an integer in an interval of length x that you can write as a sum of two squares. In a sense, what's the maximum number of ways you can write an integer m in a given range as a sum of two squares? And it's a classical result that you can find an integer m that you can write in at least this many ways. This e to the constant times log of x over log of x. Here R2 of m is this classical sum of two square functions, which counts the number of order pairs AB integers such that m is a squared plus b squared. Yeah, I say this was probably known before, well, before Ramanujan, because it really follows from classical formulas about what this function is, and such formulas were previously known to Euler, Gauss, and definitely Jacobi. So for example, recall if P is a prime that's 1 mod 4, there's actually a unique way to write P as a sum of two squares if up to possibly swapping A and B and negating A or negating B. So just the normalization, the usual normalization, the R2 of M is equal to A. When M is written like this in its prime factorization, the P's are the factors congruent with 1 mod 4, the Q's are congruent with 3 mod 4. We know that this function has this product formula. It's 4 times a product of expression that have to do with the exponents of the primes that are 1 mod 4. So 1 plus E1 times 1 plus E2 times 1 plus ET. With such formulas in mind, what you can do is, well, okay, it's pretty bad to pick a prime number to be m if I'm interested in maximizing R2 of m, because every prime number will have eight representations. But if I take product of 2 primes, I'll have 16 representations. Product of 3 primes, this keeps doubling. So a nice idea is maybe look at the square-free integer, a product of t primes, let's say roughly of the same size on the order of log of x. From the prime number theorem, you can pick on the order of log of x over log of x such primes. And so you get that the number of representations of the sum of two squares of the square-free integers is on the order of 4 times 2 to the t. So all the e's are 1, the exponents are 1 here. And if t is on this order, then you get this lower one. Yeah, so if you're a number theorist, look in this, you probably learned all about these two results from any standard analytic number theory textbook. But if you're maybe a combinatorialist like me, you will have first heard about these results through observations and a couple of beautiful conjectures of Erdős. So the first observation is that the first estimate about how many integers up to x can write as sum of two squares is related with the number of distinct distances that the root n by root n square grid determines. So it's very easy to see that It's completely equivalent almost, if you don't care about the constant, to the fact that if you look at the root n by root n grid, the number of distinct distances in this grid. So you look at the segments determined by pairs of points in this grid, calculate their lengths, the number of distinct lengths you will see is on the order of a constant times n over square root of log of n. And this inspired Erdős to formulate a beautiful conjecture known as the distinct distances conjecture, which says that any set of endpoints in R2, no matter what, if you record the lengths of the segments determined by the pairs of points in P, this number should be minimized for any set P by this n over square root of log of n. And this was in a celebrated paper from 16 years ago now. Gut and Katz nearly solved this conjecture, showing that this is true with log of n instead of square root of log of n, which is an interesting result even in the root n by root n grid. It's not a complete trivial number theory exercise to prove that there are at least this many integers up to n that you can write as sum of two squares. Anyway, the second observation is that the Ramanujan fact about the maximum value of the function R2 of m in the interval can also translate nicely in the geometric context. Namely, this can be interpreted as saying that if you look at the root n by root n square grid, then some distance, some length of a segment will be appearing many times, at least as many times as this n times this exponential that you saw before. And this also inspired Erdős to formulate what's known as the unit distance conjecture. So if you scale a bit this grid, then you get a configuration with endpoints in the unit plane where the number of unit distances is at least this. And Erdős conjecture that this might could be the right order of magnitude, namely any set of endpoints in R2 should have at most n to the 1 plus little of 1 unit distances. And the best known upper bound for this problem is n to the 4/3, going back to work of Spencer, Semi, and Trotter from '84. As maybe everyone knows, even my neighbors know, this conjecture got famously disproven a few days. Okay, now it's been almost 2 months by OpenAI on May 20th. 2026, a day which I've been told the mathematician will remember. I think it will be math before Math 20th and May 20th and math after May 20th, maybe. So in this breakthrough work, yeah, OpenAI managed to construct a set of endpoints, in some sense, very much like the root n by root n square grid, but where a distance repeats itself at least n to the 1.1 times. So a polynomial improvement over this Ramanujan type saving. And this, I won't really talk anything serious about the construction, except that this is really a number theory result. So it comes from amplifying this idea to kind of add one prime at a time, and just amplify instead vertically by using bounded root discriminant number fields. Anyway, what I thought I would do for the rest of the talk is actually try to salvage a little bit this old Ramanujan estimate and try to convince you that there's actually quite a lot of interesting arithmetic content still behind it that's relevant to other problems and even still to this unit distance problem that the juice hasn't been all squeezed out of it. And I thought maybe in the interest of time, since it's a short talk, I would do it through, rather than trying to talk philosophy, to do it through a couple of examples, perhaps examples related to Sidon sets, because these are, I think, some favorites here. They appeared in a few talks already. So here's a problem, concrete question of Erdős from the 80s. What's the size of the largest Sidon set and the first set of n perfect squares? A Sidon set, I recall, it's a set that doesn't have non-trivial solution to an equation like this, a plus b equals c plus d. So it's a funny problem. You can get the handle on it right away, especially after the previous discussion, right? If A is my Sidon set, I can look at a plus a. This grows quadratically in A. But then on the other hand, a plus a is confined into some interval of length twice n squared. So automatically a plus a has size at most twice n squared. In fact, you can do even better, because by design, if a is a set of squares, the elements of a plus a, they're sums of two squares, and they are at most 2n squared. And so from this Landau-Ramanujan estimate, there are at most this many integers in this range that are sums of two squares. So this converts easily in the upper bound for a of n over log n to the 1/4. This has been improved not too long ago by Hansen. So this log of n to the 1/4 became log of n to the 1/2. But yeah, it's been an interesting question whether one can do better than this. The lower bound construction is quite far off. So in a paper of Alon and Erdos from early 80s, they noticed that if you take a random set of the first n squares and you do a probabilistic deletion argument, you get a construction that's on the order of n to the 2/3, perhaps divided by some logarithmic terms. And then it was subsequently improved by Thiele. He removed the log terms. So now there are constructions of n to the 2/3, but as you see, there's a big gap. Yeah, so our first result in the story is an improvement of the upper bound. So this log of n to the 1/4 and then later 1/2 can be improved. And turns out you can improve it by this Ramanujan type saving. That's from the second analytic number theory estimate, not the first one. A bit curious. Yeah, I'll say a few things about the result. Maybe perhaps one line to get started with is the main driving force. So what's so special about the squares that will be used is that they're really ill-distributed modulo primes. Any prime you pick, the squares occupy about half of the residue classes mod P. And so the result actually is a bit more general than that. I won't really get into it, but for example, Helvogata and Venkatesh have this notion of what it means to be alpha ill-distributed set. Let's say A is inside the interval 1 atom alpha ill-distributed if you look at the residues of the elements from A mod P for some prime P, then the size of the set is at most alpha times P. So alpha is some number that's strictly less than 1. I'll say that A is alpha ill-distributed if the residues occupied by A mod P are bound, they're at most alpha times P in size for every prime P. In particular, if A is a set of perfect squares, you can take alpha to be 1/2. Then our result is a bit more general. So it says that if A is a Sidon set in the interval 1 up to M, that's alpha ill-distributed, then A has size a bit less than the square root barrier. So A has size almost square root of M times a saving that is very similar to this Ramanujan saving, and there's a dependence on alpha that's emphasized here. This can be put in context if I had more time to talk about Sidon sets. So there are several results, interesting results about dense Sidon sets in 1 up to M. So Sidon sets of size roughly on the order of M to the 1/2 have been proved to be equidistributed in arithmetic progressions, in Bohr sets, and things like this. Nice works of Lindstrom, Kolontzakis, and maybe Ortega Prendeville, and so on. So Fourier uniformity in dense Sidon sets. This is some kind of result in this period, but I want to maybe get into this. What I thought I would do, I don't know how I'm doing with time. Okay. Let's tell you some things about the proof. In some senses, the proof that got everything started. I don't know how much. Actually, the proof is very simple. It would fit in like 2 slides. So what do you do actually to prove an upper bound like this for Sidon sets in the perfect squares? So it's gonna be the following setup. I am gonna choose primes on the order of log n, let's say in this dyadic interval, and I pick this many of them. Again, I can do it because of the prime number theorem. And I'm gonna choose a square-free integer, p1 times p2 times pt, which is gonna be at most n if you choose the constants right. And the main idea is to look at the following quantity. I call this collision statistic. It's gonna be the number of pairs of elements in A that have the same residue class mod D, where D is this square-free number. There's some very simple observations you can write about it. Maybe just here's one. We have an interesting upper bound for this psi of A. This psi of A, well, okay, what's an upper bound for a number of such pairs? If I have a pair like this, A congruent with B mod D, well, D must divide A minus B. Okay, and A minus B, they're elements in A, and remember, A is a subset of the perfect squares. So I know the range of A minus B is between minus n squared and plus n squared. So there are 2 times n squared options for what A minus B could be, right? Actually, 2n squared divided by D, right? Because there must be multiples of D. So there are at most this many eligible multiples of D in this range where A minus B lands. And the Sidonicity of the set A tells me that A minus B can only be represented once, at most once as one of these multiples. I won't have 2 different differences, A minus B, achieving the same multiple. You have to add an extra term for A for the diagonal terms. A multiple of D is also 0, and then you can have A equals B for any. You can have the diagonal contribution. So the psi of A is at most n squared over D. To lower bound this, a natural thing to do is to split A based on the residues that the elements from A occupy, mod D. So A of lambda means the set of elements in A that have residue lambda mod D. And then it's easy to see that this psi of A is the sum of the squares of the cardinalities of these sets. Right? Two elements in A have the same, having the same residue lambda mod D means that they're congruent themselves mod D. And you sum over all the possible congruence classes. You can lower bound this using Cauchy-Schwarz, right? The sum of the cardinalities is equal to the size of A. And the number of terms in the sum is the number of occupied residue classes mod D. This is where the main observation will kick in. We have a non-trivial upper bound on what R is, right? Since A is a set of perfect squares, these occupy half of the residue classes modulo each pi that is in the factorization of the square free integer D. So in particular, R is at most the product of these factors, pi plus 1 over 2, over all the indices from the factorization, which is at most d over 2 the t. So A doesn't occupy too many different residue classes mod d. Out of the total d of them, it's easy to check that there are most d over 2 to the t of them that are occupied. So the number of terms here in this Cauchy-Schwarz is interesting. If you put the upper bound and the lower bound together, you get this. Right. So that's sort of the full proof. It's again, as you see, some kind of version of this. Well, it's related, right, to this proof I sketched for the Ramanujan estimate from my first slide. It again goes by kind of picking one prime horizontally at a time and increasing the value of d in this argument. And yeah, this sort of idea to turn kind of local information into local congruence defects into global information via Chinese remainder theorem. Yeah, it turns out to have a ton of different applications. And the rest of the time, I'll just kind of throw in a couple of different directions that one can get into using such ideas. So one natural one is, okay, one can say something about Sidon sets and the squares. What about if you replace the squares with the cubes and higher powers? And this in fact came up. You run very quickly into many interesting problems. So for example, a result we proved in this direction is about BK sets. A set A is a BK set if this equation in 2K variables doesn't have any non-trivial solutions. Okay, so Sidon sets are the case K equals 2. But it makes sense to talk about B3 sets, B4 sets, and so on. In particular, if you look at B3 sets in the first n cubes, perfect cubes, turns out you can say that A has size at most n divided by this arithmetic factor. E to the is not quite the same factor as before. It's a constant times root log n over log n. However, this is a much more difficult result. So I just wanted to, I put it in red, and it's actually one of the most serious results in the paper, if not the most serious result in the paper. Even the qualitative result that B3 sets inside the first n cubes are sparse, so a little of n result is new for this problem. And it's a bit surprising in some sense, because if you look a bit at the proof before, it really actually took advantage of the fact that if k equals 2, I can rewrite an equation, a Sidon equation, a1 plus a2 equals b1 plus b, as a difference equation. And I sort of leverage the fact that I have this difference equality. When I have this equation for a k equals 3, there's no reasonable way to write it as a difference equation, so sort of the proof breaks. Also, a bit more seriously, there's no kind of easy saving that one can do for sums of 3 cubes. So this is a more serious reason. Unlike for sums of 2 squares, sums of 3 cubes are conjectured to occupy actually a positive proportion of the integers. It's actually a classical problem in analytic number theory. So for example, if you just look at the triple sum, a plus a, and try to leverage the fact that it's contained in this interval, 3 times n cubed, well, and use the fact a plus a grows at least as large as a cubed, you cannot really hope to get a cheap saving by just kind of looking at the density of the number. You can write a sum of 3 cubes. So this is sort of a complementary result to this conjecture. I won't, since I'm kind of doing badly with time, I won't say anything about the proof, but yeah, the proof uses sort of many different ideas, kind of an entropy version of this previous argument and kind of cool local input uh, from, uh, from algebraic number theory. There's also a result about before sets in the sets of forced power. So again, no previous little O of n qualitative result was known. We get a saving here, an effective saving, but a bit worse. So it's a power of log n. We don't have any such result for fifth powers. And perhaps it's not really a coincidence. For fifth powers, it's already been mentioned, I think, by Hegevari in the previous talk. For fifth power, some interesting things are happening. For example, it's a classical problem that maybe the set of n fifth powers is a Sidon set itself. And it's kind of wide open. So this kind of arithmetic saving that we get gets worse and worse and starts getting trivial at k equals 5. Anyway, enough about Sidon sets. Let me mention two Erdos problems about distinct distances rather quickly. Here's a question by Erdos and Guy from the 70. Related, how large can you have a set of the square grid, root n by root n, if all the distinct distances, all the distances determined by A are distinct? It's kind of like a two-dimensional distance Sidon version of the problem. It's a classical problem. Easy, again, you can get an estimate. There are A choose two pairs. There are at most n over root log n distinct distances in total. A has size at most this. Can you improve on this? It's been a long-standing problem. A random deletion lower bound of n to the 1/3, big gap, like before. Another related problem, I first heard it from Jordan Ellenberg from a Math Overflow post of his, but I've discovered it's a problem of Verdosh from the 80s. How large can you have a set in the grid if there's no isosceles triangle? So before, when I forbid all repeated distances, I forbid isosceles triangles too, but I also forbid two segments that have four disjoint endpoints, you know. Here I'm allowing that. I'm only forbidding isosceles triangles and perhaps also degenerate isosceles triangles. So three APs, three equidistant points on a line. Again, very easy to see that A has size and most n over root log n, where this comes again from the first analytic number theory estimate that I talked about. The number of distinct distances determined by A is at least A minus 1. If you fix a point, the segments to the other points are all distinct in length, and there are most this many distinct distances in total. Again, can you improve on these? The lower bound is also a random construction. The second problem is a bit more subtle, actually. There's a bit more to say. That's actually not the benchmark, the right benchmark for it. There's a slightly better kind of trivial argument, still trivial argument, but a bit less trivial, is that, okay, if you have a set in the two-dimensional grid that has no isosceles triangles, every vertical line cannot have three-term arithmetic progressions. Every vertical line intersects A in a 3AP free set. So in particular, there are root n vertical lines. Each of them can intercept at most this many elements from A. That's the size of the largest 3AP free set in the interval of length root n. And using well-known theorems, nowadays really strong estimates due to Kelly and Mecca and improvements, you can get a bound of n divided by this e to the constant times log of n to the 1 over 5. So that's kind of the thing to prove. Can you be this one-dimensional reduction in some sense? Yeah, we have a result that achieves this. So essentially, the way I like to present this is that there's a nice robust version of this Ramanujan estimate that I talked about. For an inset A in R2, I can talk about the maximum multiplicity of a distance in A. So this is, I look at the distances that are determined by pairs of points in A, and I pick the distance that has the maximum number of repetitions. Turns out for any subset A of the two-dimensional grid of size at least 2, you can always pick a distance that repeats itself at least this many times. A squared over n, that's the kind of trivial pigeonhole factor. There are A squared pairs of points in A, and there's a range of at most n distances. Trivially, one distance repeats itself at least this many times, but you can gain always this arithmetic factor, which is the same arithmetic factor if A is the full square grid itself. So that this recovers the Ramanujan theorem. It has some nice consequences. So besides recovering this, if I give you a set A that doesn't have repeated distances, A has size and most root n divided by this new kind of saving rather than powers of log. If A has no isosceles triangle, then you get that A is at most this. a saving that kind of beats e to the log of n to the 1/2, which is the limit of the previous kind of trivial argument because there's this bearing construction. Anyway, I'm kind of okay, almost out of time. So I'll mention some things about kind of different in a different up direction, kind of these local to global tricks with Chinese remainder theorem and kind of some local input. Turns out, yeah, you can use it for various different things. Perhaps you might say Sidon problems are very closely related to these problems about repeated distance in the grid. But here's a kind of different looking problem. And also, all problem in additive combinatorics is the Elekes-Ronyai problem. Is this question: if I give you a polynomial in two variables over the reals and two sets of n real numbers, a and b, the question is how large or how small can is the image of the Cartesian product a cross b under this polynomial map? So what's the cardinality of this? And yeah, there's some easy examples. If you take a and b to be the interval of numbers from 1 up to n, and the polynomial to be x plus y, then this image can be linear in n. Similarly, if a and b are geometric progressions, and f is x times y, then this can also be linear in n. That's sort of a well-known problem that if f is neither additive, so nothing like x plus y, or nothing like this x times y, then the size of this set, the image set of a cross b under f, must grow nearly quadratically. So at least as large as n to the 2 minus little o of 1 for any two sets a and b of size n. This is a problem that it's sort of at the intersection of additive combinatorics and incidence geometry. Various particular cases of this question have to do with distinct distances problems. It's not quite far from the previous topic in some sense. Yeah, it's called Elekes-Ronyai problem because Elekes-Ronyai proved first that if f doesn't have these forms, then the size of the image set grows superlinearly in n. Then this has been improved. Raj, Sharir, Solimonji showed n to the 4/3, n to the 3/2, and sort of results seem like they would be converging towards and squared. But turns out, yeah, this is false, and this is of course inspired by the search for a counterexample was inspired by this amazing development on the unit distance problem. Turns out you can use this. It was a very pleasant surprise that you can use these ideas from our combinatorial sieve with Chinese remainder theorem to cook up a very natural counterexample. So it turns out there's an absolute constant C in arbitrary large sets of real numbers A, for which the image of A cross A under this specific quadratic polynomial in x and y grows subquadratically by a power. So grows at this size at most a to the 2 minus c for the specific c. Since this is not additive or multiplicative, this is a counterexample for this Elekes conjecture. And in fact, you can choose this counterexample to have small doubling. I won't really get into that. The thing I'll end with is that, yeah, so the way the story starts is that you need something like this original Erdős construction for this problem to sort of amplify by using towers of number fields, boundary root discriminant. Here, there's nothing like this available, but there's something very easy you can do that we sort of or almost already proved. Sort of the main idea is to look at the interval 1 up to n dilated by an appropriate square free number, and then to look at the values of this polynomial where x and y are sampled in here. And I claim that the image set is at most n divided by this Ramanujan saving. It's not the power saving yet, but it can be used to be amplified. Equivalently, this translates by rescaling. If I define the polynomial to be, so if I just rescale the set multiplied by d, it's like changing the polynomial to d times x plus y plus this thing, this quadratic term. And I'm asking for the image of this new polynomial on the interval cross the interval to have size at most n squared divided by this arithmetic factor. And of course, this has to do with the fact that, well, if I reduce modulo d, this equation, this is a square, and squares are ill-distributed mod primes. So I'm going to pick again my primes from some dyadic interval of size log of n. I define the square free integer to be the product of these primes. This, for each prime from each prime in this list, this is a square mod p. So it occupies half of the residue classes mod p. In particular, it occupies a proportion of 1 over 2 the t residue classes mod d from the same calculation as before. the range is at most quadratic in n because this d is at most n, and you get some kind of Ramanujan type saving, which you can then amplify with the Tower number field technology. I'll end here. There's some more results, but I'm out of time.
Thank you.
Thank you for your attention.
So I think if there are questions for Cosmin, they should go into the chat, and we will